Okay, here we are back for our lab session for our Bayesian PK/PD modeling. And what I'm going to do today here is follow up on what we were talking about before for our hands-on example number 4. Recall the last time what we did was to build the component Pascal model within the BUGSModelLibrary framework in order to make a new function that we can use in WinBUGS. And today we're going to get into then the WinBUGS implementation of the model, as well as sort of the accompanying R script to implement the whole thing. So let's go ahead and take a look at that. So remind you the model we've got. We're using the Freiberg-Carlson model for drug-induced myelosuppression. And so we've got this system of differential equations, some of which are nonlinear in there. And let me go ahead and open this up here. Let's see. Excuse me. Okay, there we are, full screen. Okay, so we've got our set of differential equations here that we've implemented. Recall that the drug finally comes in, the drug concentrations finally come into the model via this e-drug component here, and we just made that a simple model where our drug effect is just proportional to the predicted plasma concentration of MI2. And that finally shows up in our differential equations right up here. So that's where we're going to bring that into the model. And so in addition, we have to describe the model for the drug concentrations, and for that we just use the two-compartment model we had used for example number 3 in this. Which is this is just reiterating that. So just reminding you the pieces that are in here. And then we've got some other components here. We've got our inter-individual variation. Now we're using the same inter-individual variation model for the PK as we did in example 3, but we're also going to have some inter-individual variation on some of the pharmacodynamic parameters, and you can see those here. And to keep life simple, I just made those all just univariate normal distributions in this case, rather than incorporating any correlation in our inter-individual variation model there. But you could imagine making this a bit more complicated by incorporating such correlations. And then finally a log normal residual variation. Let's see, and we were bringing in some informative prior distributions, and we'll revisit these when we actually show how to program this in. But you can see we've got some particular values here. So instead of using our, these things like fairly flat normals and so on, we've now got some fairly meaningful informative priors for those pharmacodynamic parameters that for which we believe are, for the pharmacodynamic parameters that we believe are drug-independent quantities, and thus we're able to take information that was originally derived in the context of looking at the myelosuppression due to drugs other than MI2 and taking values reported in the literature from those and incorporating those into our own model without having to effectively rediscover the entire wheel for this. So we're adopting not just the model structure, but also some of the quantitative aspects that had been discovered previously. And then we've got some weakly informative priors here on drug-specific things. So, for example, that alpha, which was the parameter in the e-drug component of the model, well, that's very drug-specific. So both the population mean and the inter-individual variance component of this we're incorporating as largely non-informative here, or weakly informative. Okay, so let's go ahead and implement this thing. We're actually going to take a look at some of these. Let's see, recall from the last time, I actually should have changed that on here. We actually changed this to a different model here that we called 2CPT Newt 2 model RK45, so we'll be using that instead. But other than that, this is still relevant. So let's go take a look at those. Oops, wrong way. Okay, come on. There we go. Okay, so let's take a look at some of the bits here. Just remind you, this is the code we had worked up before for the component Pascal. Some things that we're going to need to remember when we actually build our WinBUGS code here is, I guess the main thing we need to remember is the ordering within this theta vector here. So you can see we've got a theta vector with 9 values, corresponding to several of the parameters. So we've got the first 5 are the pharmacokinetic parameters describing our 2-compartment model with first order absorption, and then the remaining 4 here are the pharmacodynamic parameters that are part of that semi-mechanistic model for our for myelosuppression. So we've got that. So we need to have the same number, and of course they actually have to be ordered in the same when we pass that theta vector in our function that we've built for WinBUGS. So let's go take a look at what the WinBUGS model itself looks like. Let's go over here. So why don't I take you? We're going to go down here into our solutions, folder here for ME hands-on 4, and let me grab the model here, ME hands-on 4.txt. Let me open that guy up. Okay. Oh, let me make it look a little prettier here. Let's see. Okay, let me also enlarge these guys a bit here. That should make it a little easier to see at your end. Maybe even a little bigger than that. Okay, I think we're okay there. Okay, so a lot of components of our model are going to be sort of same old sort of things that you've seen before. And in fact, one way you could have built this up is to actually start with the model you had for the hands-on, for our third hands-on example, and then begin adding the pharmacodynamic components to it. So for example, the way we've got our inter-individual variability brought in, of course that's what's happening inside this 1 to n subcomponent here, is we're going to have the same inter-individual variation model that we had when we did just the pharmacokinetic model, which was here we had a full block covariance matrix in here as part of our inter-individual variation for the PK, and in our model we're going to assume that the PK parameters are independent of the PD parameters here. So this you could have adopted entirely from what was in the example number 3. So that's the same as we had before, and then recall we had our 3, let me scroll back up so you see them here again. We had there we go. We had our 3 of our PD parameters were incorporating inter-individual variability just using univariate normals. So what you see right there then is being repeated right down here, where we've got our just 3 univariate normals here for our PD parameters in there. So that takes care of our inter-individual variability. So that's where that part comes in. Let me skip a bit here because we'll talk a bit about the bookkeeping, but I think it's better to have an idea of how we're going to be using our model before some of that will make any sense. And that's right down here is going to be our call to that component Pascal model that we built. So that's our new custom BUGSModelLibrary function. And I just noticed the way I have this, apparently the last time I ran it, I had used the LSODA differential equation solver. Let me change that back to the one that I showed you last time, which was using the Runge-Kutta method in here. So all I got to do is just change which thing I'm commenting out. So this is where we actually call that new function we built. So when we call that, of course, we've got to pass all our usual values in here for each one of our subjects. So we've got, your usual time, amount, rate, and so on all through here. Basically all those usual sort of non-mem style variables that are being passed into this. And then we've got a set of model parameters specific for our ith subject here. And you can see I've passed that in, and I've given it the name theta PD. And in a second I'll show you why I'm going to make a distinction between what I'm calling theta PD and theta PK. Now recall in our function, what I'm calling here theta PD actually has to include not only the parameters specific to the pharmacodynamics, we're also going to need to pass all of our pharmacokinetic parameters as part of that too. And again, just reminding you where to go here. Yeah. So in addition to the PD, as I showed here before, we've got to have our first 5 thetas have to be our PK parameters. So that has to happen in here. So that's what the theta PD is going to contain. Now, recall, let's see, when was that? That was probably, was that last lecture or 2 lectures ago? I've lost track now. When we talked about the cut function as a mechanism for doing what is essentially a type of sequential analysis, where you can, where in a context like this, we might choose to, we might prefer that the pharmacodynamic data not influence the pharmacokinetic parameter estimates. And again, the usual rationale underlying that choice would be if we have a situation where we feel we've that our pharmacokinetic model is maybe better specified and less likely to be subject to model misspecification than our pharmacodynamic model, we might be concerned that the pharmacodynamic model might inappropriately influence the pharmacokinetic parameter estimates. So if that's the case, then you might want to do the analysis sequentially, but we can do a type of sequential analysis simultaneously, somewhat paradoxical sounding sort of thing, by using the cut function as part of this. But when I showed you the cut function, I showed you a fairly simple case, a simple example where the pharmacodynamic effect depended, while the pharmacodynamic effect at a particular time depended upon the concentration at that same time, and so all I had to do is put the concentration inside of the cut function, and that would take care of that. It's a little bit messier in this case because the effect at a particular time is influenced not just by the concentration at that moment, but by the history of drug concentrations. In fact, you can sort of think of the dependence as being on a sort of weighted average of the past concentrations, the more recent ones being more weighted more heavily than those further in the past, but it makes it more difficult. You can't just put a cut function around the predicted concentration. We're going to have to do something a little bit differently, and that's going to drive the reason why instead of just calling this function once and using that for both the PK and PD modeling, I also have a second call to another function, in this case just the pharmacokinetic component in here that is going to be responsible for driving the PK model fit. Anyway, more on that in a minute here. But let me just comment that if you did not want to use the cut function, you would not need this second call that I'm showing right here, where I'm calling the two-compartment Ka model. That's only necessary in this case because of the way we're going to be using the cut function. If we chose to do a true simultaneous fit, where all of the data influences all of the parameters, then just this one call to the to our complete model, which includes both the PK and PD, would be sufficient. But we're going to complicate life instead, and we are going to incorporate the cut function, and let me show you how that's done in this case, where we can't just simply put a cut around the predicted concentration at a particular time. Let's scroll back up here where we're actually building our theta vectors. So again, up here I showed you where we did the inter-individual variation, but now we have to assign all this nonsense to the things that we're generating to our theta vectors and build the theta vectors we're going to pass to our two functions here, our PK model function and our PK-PD model function. And so some things here, let's see, where do I want to show this? Let's start with this right here, this loop. Here, where you can see I'm going from j equals 1 to 5, well, that 1 to 5 is going to take us over the PK parameters. So that's going to take us over clearance, Q, V1, V2, and Ka in here. So to create the vector here we're calling theta PK, it's actually a matrix overall, but for a particular subject it's just a vector of values. So my theta PK then, I'm going to take that, and say that I want the log of that value to equal the corresponding log theta values that we generated from our multivariate normal distribution above. And that's what I'm going to be passing to our PK model function. But then I also need those very same parameters to be passed to the PK-PD model function, and that's what's going on in the next line here. But here I've incorporated the cut function. So on the right hand side you'll see I've got the same log theta values that I have in the previous statement, but I put a cut function around them, and I'm assigning those now to theta PD, and it's that theta PD that I'm going to pass to our PK-PD model function. And that's going to accomplish what I mentioned before, which is we've got a situation then where the data, the PK data, will influence the PK parameters. In other words, the first 5 parameters also within this theta PD. So PK data is going to influence them, but because I put a cut here in front of this when I've made the assignment to theta PD, then when I use theta PD in our PK-PD model, that PD data is not going to affect the estimates of the PK parameters. Though the reverse is not true. The PK parameters will definitely influence the fit to the PD data. Okay, so we've taken care of that, but then we've got also the theta PD is also got to include our pharmacodynamic specific parameters, and you can see those assignments here. So we've got our mean transit time, our baseline ANC value. There was that gamma parameter. I'm trying to remember where that was. Actually, remind myself, I forgot what gamma comes in. Oh, okay, there it is. It's right up there. Yeah, I couldn't remember where it was. So we've got that parameters in there. And what else? Okay, the alpha, which is the parameter related to the drug effect. So all of those then are being assigned also to that theta PD vector in here. And then for both theta PK and theta PD, we have to add our F's and our T lags for all of those, one per compartment. So in the case of our PK model, there's only 3 compartments. In the case of the PD model, there's 8 in there. So we have to make these different numbers of assignments in there. So that finally generates all of our parameters there, which then the corresponding ones. So for our PK model, right here, you've got the theta PK, and then for the PK PD component, we have our theta PD in here. And then finally down here, now we've got 2 types of dependent variables. We've got the PK data, we've got our PD data. And we called the log transform PK data, log COBS, and we called the log transformed neutrophil count data log NEUT. So the statements I was just highlighting are the corresponding likelihoods. So this part right here, again, should be identical to what we had in our example 3. So you can see all that taken care of here. So you've got our log normal distribution on the concentration, or equivalently normal on the log of the concentration. We've taken care of censoring due to observations being below the limit of quantitation taken care of. Down here, the C hat quantity here, that's our model predicted concentration, and that's taken care of. Here we've got our X hat, or the amount in the central compartment, divided by the volume here, and multiplied by 1,000 to get the units right in here. So that pretty well takes care of that. The log transform, and finally a posterior prediction. And then down here for our neutrophils, a couple of things going on. First, as we had specified, we were going to use log normal residual variation, so that's in there. And in this case, there was no censoring of any kind, so we didn't have to worry about that. We've got our posterior prediction here. And then for the model predicted neutrophil count, we have this amount in compartment 8, but recall the way we wrote the differential equations, these X hats were not actually the amounts in these corresponding compartments. In this case, they were changed from baseline in those amounts, so I have to add the baseline back in. So here we've got our X hat PD for change from baseline in our neutrophil count, but then I add in the parameter that represents the model predicted value then for the baseline neutrophil count, assuming of course I put the right number right there in here. So hopefully the 7th parameter was our what we called circ 0 in the model. And then this bit down here was just taking care of a log transform again. Okay, before I go into the priors here, let me see if there's any question on this part of it. Okay, nothing so far. If you're typing, feel free to keep going here. I'll keep my eye open for it. Let me wander down to the prior distributions, because there were some aspects about the problem that were unique here, because we're actually incorporating informative priors. So it's going on our prior distributions. The first part is just the PK parameters, which is same thing we had done before in example 3, so there shouldn't be anything unique going on there. Where it gets more interesting is down here with our PD parameters. And here we can start out, we've got our drug specific parameters that we said we're going to use just weakly informative priors for those. So you can see that includes our alpha hat, which was our that's going to be our population mean for the alpha in here, and then we've got, or I guess we should call it a typical value because we're going to log transform it somewhere in there. Then we've got our variance associated with that here, our omega alpha, and then generating the corresponding precision value. But then down here is where we've got things that are a bit different, where we're incorporating our informative prior distributions in here. So let's actually step back to what we specified up here. Let's see. Okay, so we've got various quantities in here. So we're going to be using informative priors, and you can see I've got we're going to use normal distributions for priors for the log of our circ0 and log MTT and log of gamma. So that's the first three here in our list. So we're going to use normals for those quantities, but then we're going to use gammas for a couple of our variance terms, or actually more correctly, we're going to use inverse gammas for the variances, but we're going to be using gamma for the precisions in here. In other words, 1 over omega squared circ0 and 1 over omega squared MTT. And here I've got the values we're going to use written in terms of means and standard deviations. Those are going to be pretty easy to translate into normal distributions here, but it's a little bit trickier in the case of the last two, where we're going to be using gammas, which are normally not parameterized in terms of means and standard deviations. Okay, so let's go back. Okay, I'm pushing the wrong button. There we go. Okay, so a lot of this is going on down here, and let's see, which did I actually do here and which do I do in the R script? Okay, I'll have to show you some of that stuff that's going on in the R script. But what you can see here is, for example, I've got the log of MTT hat, log of circ0 hat, and log gamma are all written in terms of normal distributions, where you can see I have named quantities for the means and the precisions here. Now that's sort of user choice there. For this, I could have just hard-coded the numbers in rather than using names like this. What I've chosen instead to do is I've used names, and I actually calculate those values inside of the R script and then pass them as part of the data set. So these quantities that you see here, like log MTT hat prior mean, that's a quantity that's going to be specified in the data set, and I build that out in the R script when I create the data set there. So I'll show you that in a second. Similarly, as I was pointing out, in the case of the gamma distributions, they're parameterized in terms of two parameters, but those two parameters are not a mean and a standard deviation, or a mean and a precision, or anything. They are related to the means and variances of those distributions, but they are not equivalent to them. So I'll show you how to do that again in the R script. So inside the R script, I calculate the appropriate quantity here, this tau MTT prior alpha and tau MTT prior beta, and again pass those as parameters. And let's see what else here. I guess there were a couple others that were, what do we got? Okay, this is this is for our residual component here. Actually, do I even use that one? I don't think I do. DF Newt. I think that was a vestigial thing for when I was playing with a T distribution for the residual yeah, you can ignore the df newt here. You'll see some code that I've commented out here. At one point I was playing around with using a t distribution that allows for fatter tails than the normal distribution does in our residual variation. So that's just an illustration of how you can end up with something other than normals in here, but I don't actually use it so in the normals, so you can ignore the this df newt line here. In fact, I should probably just comment it out because we're not actually using it here. Okay, let's see. I think that's most of the story about the script itself here. Let's open up the corresponding R script where we generate some of these things. Okay, let's see. Okay, again, let me make that a bit bigger. Okay, so here's our R script. Most of the beginning stuff, of course, is the usual nonsense you've seen before. We specify the model name up on top. Most of the rest of this stuff is pretty much ignorable, it's stuff that's worth learning, but it's the same as you've seen in the previous examples. Let's see, I specified the limited quantitation like we've done before. Read in the data here. Oh, I see, I left this bit here. Actually, we ended up cutting back the number of subjects, so this was probably overkill. This happened to be code I had put in there just to speed up the run in here. To actually do the full data set, you should comment out this bit right here. In fact, I'll do that right now. So to do the full data set, just comment out those 3 lines, and I think we're all set. And the rest of it is some various data management, converting dots to NAs. You've seen that before. And what do we got? And some bits here to create unique IDs for all the subjects. Let's see in here. Just remembered, I think there was an error I had discovered in this recently. Did I? Oh no, that's taken care of right there. I've apparently made the error in something else, not in that one. Okay, so most of that is same old, same old. Okay, here we go. Here's the part that's more unique, is where we're starting to bring in the informative priors. So let's see. Okay, here we go. So if you look at these numbers, assuming I did them correctly, if you compare those to what we have here, they should match up to the items in this table. So here you can see I've got for our mean baseline value here and the corresponding coefficient of variation, same thing for our mean transit time, then for gamma, and then finally I've got these means and standard deviations for our precisions in here. So we're going to need to convert those to the appropriate alpha and gamma parameters. So let's see what we did in our data set. You can see where this is happening. Most of the data set is same stuff you've seen before. Let's see, where does something, okay, where the stuff that's somewhat new coming in is when we finally come down to here. This last bit down here. So some of these are pretty straight ahead. The mean, our prior mean for that log of circ 0 is just the log of that circ 0 hat. And then for our precision, we just have to take 1 over that CV value squared. And we do that same thing for MTT and gamma. That same story. Where it's a little different is with the circ 0. In here we have to do a little bit different calculation, and let me make sure I actually did it. Or did I do it right here? Yeah, okay. Just making sure. Now, these come from the fact that the mean of a gamma distribution is equals, first of all, there's two parameters. Let's call them alpha and beta of our gamma parameter. The mean of the gamma distribution is alpha over beta. And the variance, if I remember correctly, is alpha over beta squared. So if you take those two equations and solve them for alpha and beta, you get these things here. So I end up with this. So for my alpha here, I've just got that, my mean of the precision over its standard deviation and that entire quantity squared. But then for the beta parameter, I take the mean divided by just the precision squared, so no parentheses around that one. And we do the same then for our MTT. That then serves as specifying our informative priors then for all of those components. Let's see, I was trying to think if there was anything else new in the rest of the code, beyond just having to specify values. Probably not a lot here. Notice in this one here, I actually, for a couple of the parameters, I actually used, for parameters where we had informative priors, for the initial estimates, I actually sampled from those informative priors. So you can see that right through here. So I'm actually using those informative priors, including using the gamma distributions for the precisions in these two lines right here. And that just seemed like fairly plausible values to use then to construct initial estimates. And then the rest of the story, I think, is pretty much boilerplate, other than maybe some details in the way we present the posterior predictions in here. And that, I guess, let's go ahead and wander off to the results. Now recall this was done using only half the data, which was probably stretching things, because that puts us with what, only I think 4 individuals per treatment arm within this. We see a familiar problem here where we've got some convergence problems associated with Ka, and if we look down the stream, you'll see a parallel problem with V1 in here. That's still one of my favorite problems to solve, is to find a better parameterization to prevent those kinds of problems. But for now, what this is saying is at minimum you need to run more samples to get good pharmacokinetic parameter estimates in here. Fortunately, that particular convergence problem doesn't severely influence the posterior predictions and the plasma concentrations, and as a result, when we start looking at our PD parameters, you don't see the same sort of convergence problems, though for at least some of them we do have, it's pretty evident we need to run more samples because of some large autocorrelation. So for example, Circ0 hat is fairly clean. I'd like maybe a tighter, fuzzier caterpillar here, but it's not too bad, at least for a preliminary look at the data. So you've got that. Alpha hat, however, you can see the autocorrelation is pretty severe. And looking at that, I'm immediately inclined to say I'm going to need at least on the order of 10 times more samples in order to get adequate precision there. Let's see what else we got. Our various variance parameters, most of them not too bad. A bit of autocorrelation in this omega MTT here, though, as well as the omega alpha. And in fact, again, for MTT, we've got a fair amount of autocorrelation. And actually, let me take a look something here. Yeah, I think if we looked, we'd probably find there's a fair amount of correlation between alpha and MTT from the looks of things. So we can either run a bunch more samples or explore some reparameterizations to try and improve that. In this case, since they're reasonably well behaved in the sense that these things are at least converged to the point where they're kind of, we've got all three chains kind of intermingle with each other, I'd probably just run more samples. Okay, and then we're looking at a bunch of the variance estimates and covariances in here, and the ones for PK are suffering from the difficulties we had, particularly with KA and V1. Let's see, looking for any new news here. Yeah, you can see particularly the V1 is showing the same pattern as the KA. In here, our residual variance terms look clean. So it's not good enough for production work, but for exploratory work, this would probably be okay as a first step to explore your model. But I certainly wouldn't want to report any of the PK parameters out of it. And I'm just getting our usual marginal posteriors here. Here we're looking at the PK predictions in here, so we're looking at these are individual predictions in here, and of course, not surprisingly, well, for the zero dose, it's kind of meaningless. Let's move on to the different dose levels here. So we got our 5 milligram dose, and you can see things are, in terms of fitting the data, is pretty clean. We just haven't done a good job of estimating a couple of the parameters. Let's move on to the PD, since that's the new stuff. Here's our placebo data in here, and you can see the credible intervals here are pretty consistent with the observed data for the various subjects. Of course, under our model essentially assumes that in the absence of drug, that the predicted neutrophil counts are just going to stay constant, and that's of course basically what you're looking at here. Starting to see a little bit of movement at the lowest doses, but the drug effect doesn't really become real evident until we get here around 20 milligrams, and the effects are starting to become far more apparent. You can see the drop in both the predicted and observed concentrations, and in particular the model seems to be capable of picking it up. In here, of course, again, we're looking at individual fits, so we've got parameters here that have been tailored to individual subjects in here, but at least so far things are looking pretty consistent. And here I think that's the highest dose, so you can see the predicted drug effect pretty clearly here. Then it walks through the population predictions. Of course, now the prediction intervals are wider since they also include the inter-individual variation in here. We're in the PD section. Let's wander up to higher doses. And you can see there is a fair amount of variation amongst individuals, as well as some residual variation here. But for the most part, the model still seems to be picking things up, albeit with a fair amount of noise here. The fact that these bounds here are kind of rough here is also consistent with the fact that we probably need to draw more samples here. That's part of the story. The other part of the story is that the number of individuals contributing to our estimates of inter-individual variation are quite small. But having said that, the one thing that would be interesting to look at as an exercise would be to see, well, what happens if I did not use informative priors for some of the parameters. I'm guessing this would look quite a bit poor, but I haven't actually attempted that exercise. These are attempts at doing a posterior predictive check where we plot both the observed and model predicted median, and let's say I use the median 5th and 95th quantiles here. In the case where we've only got 4 observations per or 4 individuals per treatment arm, I actually wouldn't recommend this particular diagnostic, because the problem is you end up with extreme overlaps amongst the quantiles, and it's not very sensitive in here. And also the observed quantiles are, the median, I suppose, is somewhat meaningful, but the 5th and 95th quantiles is kind of a silly concept when you only have 4 individuals in a treatment arm. So I'd kind of ignore these. They were diagnostics I left in, related in part to when we were using the larger data set for the PK parameters. But in this context, again, they're probably not very meaningful. So that's pretty much the whole tale, I think, on this, other than actually going through and running it. You might want to go ahead and run it with the full data set and see if some of the fit improves. Also run it using more samples, although it's been a while since I actually ran this myself. I think that was back this summer. I know it does take a fair amount of time, and I don't remember off the top of my head how long it took, but it would certainly be in terms of hours in order to do the run. Trying to think if there's any other story to tell around this example. I guess in some ways, some of these, the story gets more interesting if we actually use it in more of an application. Here we've only fitted the model. It might be more interesting to start use the model than to ask questions like, what would be the highest dose that would produce tolerably small changes in the neutrophil counts, for example, and then you could compare that to, okay, well, what is the what dose produces minimally clinically relevant improvements in I forget what indication were we going after for this. Now I've forgotten, for our ME2. But what would produce suitable efficacy, and is there and is the dose that produces efficacy within a range that produces acceptable changes in the neutrophil counts. So again, I'll take a breath here, see if there's any questions before we close out. Okay, well, if no questions here, I guess I'll say goodbye for now until we have another session on Monday. Look forward to seeing you then. Okay, bye for now.